Welcome to the deep dive. Today we're digging into quite an interesting shift happening in AI efficiency. It seems the focus is moving away from the model itself.
And more towards the data,
Right.
specifically the amount of data, the tokens being processed.
Right, and our sources for this deep dive seem to center around one specific research paper.
That's right. It's titled Shifting AI Efficiency from Model-Centric to Data-Centric Compression. And our goal here really is to unpack why this shift is occurring, understand what this token compression actually is, and, well, why it might be so important for making AI more efficient down the road.
Okay, because for a good while it felt like the main path to better AI was just scale up the model,
Yeah.
right? More
Oh, it's
parameters.
definitely the dominant approach, especially, say, from 2022 into 2024. Performance gains were heavily tied to increasing model size.
Which naturally led to research on how to handle those massive models.
hmm Things like model-centric compression, quantization, pruning, distillation, low-rank decomposition,
Yeah.
ways to make these huge models a bit more manageable.
But it sounds like we're hitting some walls with that approach. Hardware limitations, maybe?
Partly hardware, but also the sheer computational load
Right.
when models need to process really long sequences. Think ultra-long text documents, super high-res images, extended video feeds.
That processing becomes the real bottleneck.
It does, especially because of how attention mechanisms work. And that brings us to the core idea in the paper, the need to shift focus. Less on compressing the model, more on compressing the tokens.
Data-centric compression with token compression is a key technique.
That's the argument.
All right, let's get into that shift. Why now? What really pushed the focus from the model to the data?
Well, the paper suggests that around mid-2024, the explosive growth in model size, we were seeing models approaching, a trillion parameters, it started to plateau somewhat.
Okay, so model size growth slowed.
Relatively speaking, yes. But at the same time, the length of the data sequences models were expected to handle just kept growing exponentially.
Ugh. So the challenge wasn't just the model's complexity anymore, but the sheer volume of tokens it needed to juggle for a single task.
That became the dominant factor.
Can you give some examples? How much have the sequence lengths actually increased?
Sure. Take language models. Llama 1 handled maybe 2,000 tokens of context now. You have models like Llama 4 Scout reportedly managing 10 million tokens.
10 million, that's a massive jump.
It is. And it enables things like very deep reasoning chains like DeepSeek R1 or complex multi-agent systems where agents need a lot of shared context.
And this isn't just text, right? Vision models too.
Definitely. In multimodal models, the ones handling images and text, we went from processing standard like 224 by 224 pixel images.
Like an LLM.
Right. To now handling 4K resolution images with things like Intern VL3 and even processing video frame by frame up to 8K frames for models like Video XL Pro.
Wow, and image generation.
Similar story. Stable diffusion started around 512 by 512 pixels. Now you have models like PixArt Sigma generating 4K images and Sora generating potentially hour-long videos. All of these require vastly more tokens to represent the information.
So across the board language, vision generation, the amount of data per input, the number of tokens has just exploded.
It really has.
And this directly leads to that computational bottleneck you mentioned.
It does. The culprit is largely the self-attention mechanism, which is fundamental to most modern architectures, especially transformers.
How does that work? Why is it such a problem?
Well, self-attention calculates how relevant every token in a sequence is to every other token. The computation required for this scales quadratically with the sequence length, n, so it's O, N, O.
Meaning if you double the sequence length, the computation doesn't just double, it quadruples.
Roughly, yes. And when you go from a few thousand tokens to millions, you can see how the computational cost just becomes immense. It's the dominant cost factor for these long sequences.
Okay, I see. So the models got big, but then the inputs got massive. And the way models process those inputs just couldn't keep up efficiently.
That's a good way to put it.
Which brings us back to data-centric compression, and specifically token compression. How does that tackle the problem differently?
Instead of tweaking the model architecture or parameters, token compression focuses directly on the input token sequence itself.
Trying to make the input shorter before the model even does the heavy lifting.
Essentially, yes. It tries to identify and reduce redundancy within that input sequence during processing, often without needing to retrain the model or change its core design.
So find the less important bits of information in the input and deal with them somehow. How does it figure out which tokens are less important?
That's the first stage, the compression criteria. You need some way to score each token, figure out its importance or redundancy.
And how do you score them?
The paper groups the methods into two broad categories. parametric and non-parametrics.
Parametric meaning using more AI.
Sort of. Parametric methods use auxiliary networks, smaller helper networks, to do the scoring. These can be training aware, where the helper network is trained alongside the main model, or training free, where you just use a pre-trained network for scoring.
Okay. And non-parametric.
These are methods that don't rely on extra learnable parameters.
Mm.
They might leverage calculations the main model is already doing, like looking at attention weights.
Mm.
Or they might use external calculations, heuristics, like measuring the similarity between token representations at intermediate layers.
Mm-hmm.
Think cosine similarity, things like that.
So basically, use helper AI or use clever math without extra AI to score the tokens.
That's a decent summary.
Okay, so we've scored the tokens. We know which ones are supposedly less critical. What's the next step? The compression strategy.
Right. How do you actually handle those identified tokens? The paper highlights two main approaches here: token pruning and token merging.
Pruning sounds straightforward. Just delete them.
Pretty much. If a token score is below a certain threshold, you just discard it. It's direct, reduces computation, but you obviously risk losing potentially useful information.
And merging sounds a bit more subtle.
It is. Instead of just deleting tokens, merging combines tokens that are semantically similar. It typically involves creating a new token representation that's a weighted average of the tokens being merged, with the weights often based on those important scores.
So trying to keep the essence of the information but in fewer tokens.
That's the idea. It aims to preserve information more effectively than simple pruning.
Makes sense. Now let's talk benefits. What does token compression actually achieve, both during training and when the model is being used for inference?
Okay, during the training stage, there are potentially two kinds of benefits. First, enhancing training quality.
How so? By reducing tokens.
Well, you can use token manipulation as a form of data augmentation. Maybe swapping some image tokens or replacing text tokens with synonyms to increase data diversity. Or, more directly, you can use scoring to filter out low-quality or noisy tokens from the training data itself.
Ah, so cleaning up the training data, focusing the model on the good stuff.
Right. Reducing noise and redundancy can potentially lead to a better trained model. The second benefit is increasing training efficiency.
This seems more obvious. Fewer tokens means faster training.
Yes, directly reducing the number of tokens processed saves compute time and memory. And remember that O(n) object cost for transformers, if you reduce the sequence length from n down to m tokens.
The computation saving is quadratic, right? Like MRN.
Proportional to that, yes.
Yeah.
So O(n)RN, and the memory saving is linear, proportional to m. This translates to faster training runs and potentially allows for larger batch sizes, further speeding things up.
That quadratic reduction in computation sounds really significant, especially for those super long sequences.
It can be a very big deal.
Okay, that's training. What about inference time? When the model is actually doing its job?
Similar benefits, really. You get decreased computational complexity, again, potentially a quadratic speedup, especially if you use those non-parametric methods that don't add much overhead themselves.
Faster answers from the AI.
Faster processing, yes, and reduce memory usage, too.
Yeah.
The memory needed for the computation scales down linearly. And importantly for large language models, the memory needed for the KV cache also reduces linearly.
The KV cache. That's the attention mechanism's short-term memory, right?
You can think of it that way. It stores key and value states for previous tokens. Fewer tokens mean a smaller cache, which is a major memory consumer in LLMs during inference.
And these speed and memory benefits during inference are crucial for
Real-time applications. Think about interactive systems, UI agents, chatbots, autonomous driving systems, processing sensor data constantly, embodied AI robots interacting with the world. They need fast responses based on continuous streams of input. Token compression could be key there.
So potentially making things like self-driving cars more responsive and efficient.
That's one potential application area where it could be very beneficial.
The paper also seems quite bullish on the overall advantages. What makes token compression so compelling, according to the authors?
They list about 5 key points. First, its universal applicability. Token redundancy isn't unique to text. It happens in images, audio, video too. So the technique is broadly relevant.
Okay, it's versatile.
Second, the dual-phase efficiency. It helps in both training and inference, often with minimal impact on the final accuracy.
Good point. And third?
Third, architectural compatibility. It's generally orthogonal to model compression techniques. You can potentially do both compress the model and compress the data, and it plays nicely with existing hardware and systems.
Doesn't require totally new kinds of computers or anything?
Generally not. Fourth, they mention low implementation costs. Modern deep learning frameworks often handle variable sequence lengths quite well, so integrating some compression methods might not require massive code changes or retraining, at least in some cases.
Easier to adopt, potentially.
And finally, the fifth point circles back to that quadratic game. Because self-attention is O(n) fort, any reduction in n through token compression can yield disproportionately large computational savings.
Right, the ON makes token reduction especially powerful, but it's not all smooth sailing, is it? The paper mentions challenges too.
Oh, definitely. It's an active area of research, and there are significant hurdles. One major one is performance degradation.
The compression makes the model worse.
It can, yeah. There are issues with the methods themselves. For example, relying solely on attention scores to decide importance can be unreliable. There seems to be a bias where tokens later in a sequence get higher scores, regardless of actual importance.
Which might lead to keeping the wrong tokens, especially in images, maybe.
That's been observed. And somewhat surprisingly, the paper notes that some attention-based pruning methods have actually underperformed compared to simpler approaches like random pruning or just basic pooling, particularly for image understanding tasks.
Huh. So the sophisticated approach isn't always better.
It seems not, currently. There are also inherent limitations depending on the task. Token compression seems to struggle with visual grounding tasks in multimodal models, where you need precise links between text and image regions.
Okay.
It can also lose critical information in dense documents, like OCR tasks, or disrupt the temporal flow needed for automatic speech recognition or translation. High compression ratios, especially, can really hurt performance in cross-lingual translation.
So information loss is a real risk, especially for tasks needing fine-grained detail or sequential coherence.
It is. And another challenge is getting the right token representation after compression.
What do you mean?
Well, methods focused on just reducing redundancy might keep tokens that let you reconstruct the original input well. But these tokens might not be very useful for actually discriminating between different concepts, which is what you need for classification tasks.
Ah, they keep the fluff but lose the signal.
Could be. Conversely, methods that score tokens based on importance for one specific task might create a compressed representation that's biased towards that task and doesn't generalize well to other things you might want the model to do later.
So finding that sweet spot representation is tricky.
It is. And then there's the whole issue of fair comparison.
How do we measure if one compression method is truly better than another?
It's harder than it sounds.
Yeah.
Metrics like FLOPs saved or the compression ratio don't always tell the full story about actual runtime speedup.
Why not?
Factors like how well a method integrates with optimized libraries like flash tension matter. Also, some methods apply compression progressively, which adds overhead not captured by simple FLOP counts. The paper argues we really need to focus more on measuring wall clock latency.
Real-world speed.
Yes. Plus, the standard benchmarks we use to test AI models might not be suitable for evaluating token compression effectively.
Yep.
Some benchmarks might not penalize information loss enough, or they lack task diversity. You might see paradoxical results where compression seems to improve performance, or it causes very little degradation, simply because the benchmark isn't sensitive to the kind of information being lost.
Okay, so we need better ways to test these methods on tasks that really challenge them.
That seems to be the case.
Given these challenges, what does the paper suggest for future work? Where does this field go next?
A couple of key directions. One is exploring data-centric and model-centric compression together. Co-development.
Combining the two approaches.
Exactly. Think about applying token compression on top of a model that's already been quantized or pruned, or using insights from token compression, like which tokens are consistently deemed important to help guide model pruning decisions. Maybe use the gradients or attention scores from neurons focused on important tokens to guide which other neurons to keep.
Finding synergies between the two compression paradigms.
That's the hope. The other major area is developing dedicated benchmarks specifically for token compression.
Benchmarks designed to reveal the weaknesses we just talked about.
Right. They need to cover diverse domains, include tasks known to be challenging for compression, like detailed OCR or speech recognition, and crucially, evaluate both task performance and actual latency side by side. We need more rigorous evaluation.
It certainly sounds like this shift towards data-centric compression, especially token compression, is a really important trend to watch in AI efficiency.
It does seem that way. As context lengths continue to explode and become that primary computational bottleneck, finding smart ways to compress the input data at the token level looks increasingly crucial for building AI systems that are both powerful and, well, practical to run.
Yeah, it really makes you think, doesn't it? How this focus on data efficiency might reshape how models are trained, how they're deployed. You start wondering, where could this make the biggest difference? What applications really stand to gain from processing massive amounts of data much faster? Definitely food for thought. Thanks for breaking that down for us.